Good morning, students. Today we are going to see the distorted geometry in the octahedral complexes. That is, tetragonal distortion of octahedral complexes. That is, Jahn-Teller distortion. The irregular geometry which will be occurs in octahedral complexes. It is explained by Jahn and Teller, and thus it is called as Jahn-Teller distortion. The regular shape of an octahedral complex is distorted if d orbitals of the central metal ion are not occupied symmetrically, because the symmetry of the electrical field is upset. This occurs when you have under T2G and EG sets of orbitals that contains the number of electrons which will be neither completely filled nor half filled. The set of d orbitals is have the effect of such a lack of symmetry on the geometry of the complex. This is known as Jahn-Teller effect. The Jahn-Teller theorem states that any non-linear molecular system in a degenerate electronic state will be unstable and will undergo some kind of distortion to lower symmetry, remove the degeneracy and lower the energy of the system. If the d electrons are symmetrically arranged with respect to an octahedral ligand field, they will repel all 6 ligands equally and a completely regular octahedral structure will be formed. The symmetrical arrangement of d electrons in T2G and EG orbitals in strong and weak crystal field is shown here. See, if D0 system all orbitals are empty, it is symmetrical. If D3 system, see, there are the 3 electrons in T2G orbitals which are symmetrical, and there is no any electron in EG orbital, it is also symmetrical. See, D5 system in weak field, each orbital contains 1 electron and it is symmetrical in case of T2G and EG also. D6 system in strong field, all electrons will be get paired into the T2G, so each orbital have the 2 electrons in T2G set, it is symmetrical. EG orbitals having no electrons, both EG orbitals are the symmetrical. Then D8 system, either in weak or strong. See, there are the T2G6 and EG2, that means 3 T2G orbitals have the 2 electrons and EG orbitals have the 2 electrons, they are symmetrically filled. And last one is the D10, which is the T2G orbitals are completely filled, EG orbitals are completely filled, and it shows the symmetry. And for that we have the examples of that particularly regular octahedral complexes for D0 system, D3 system, D5 system, D6 system in strong field, D8 system and D10 system. Thus, with these configuration, we have the symmetry and we have the regular octahedral complexes. But other than these, if there is the irregular or unsymmetrical filling of electrons, then that will be results in the distortion, and we are going to see that distortion. It then follows all the other arrangement have unsymmetrical arrangement of electrons. See here we have the D4 system. This D4 system, there is the in weak field. See, T2G have 3 electrons and EG have 1 electrons. Here T2G orbitals are symmetrically filled, but EG orbitals are unsymmetrically filled. That means in case of the EG orbitals, there is single electron in one orbital and another orbital is empty. This filling of electron is unsymmetrical. So here EG orbitals, that means particularly there is dx square y in and y square, dx square minus y square and dz square orbitals, they are unsymmetrically filled and it will be affect d7 system in strong field. See T2G 6 and EG1, here again T2G orbitals are symmetrically filled and EG orbitals are the unsymmetrically filled. We know T2G orbitals are in the plane, in the xy plane, while EG orbitals are along the xy axis as well as in the z axis. Then D9 system. D9 system in both high spin or low spin, that is either strong field or either weak field. See T2G6 and EG3. Here T2G orbitals are symmetrically filled but EG orbitals are unsymmetrically filled. In EG orbitals, one orbital have the 2 electrons and second orbital have the 1 electron. So it is unsymmetrical situation, and in that situation with these configuration and respected fields we have the distorted octahedral geometry. Since the T2G orbitals point in between the Lagrange direction and symmetric filling of these orbitals has little effect on the stereochemistry. In contrast, the EG orbitals points exactly at the direction of the ligand and hence unsymmetrical filling of the EG orbitals causes some ligands to be repelled more than the others, resulting in the significant distortion of the octahedral shape. The two EG orbitals dx square minus y square and dz square are normally degenerate, but if one of these orbital is unsymmetrically filled in an octahedral environment, this degeneracy is destroyed and the two orbitals are no more equal in energy. A pictorial idea can be laid down by considering the examples of Cu2 plus D9 system. The T2G orbitals are full. The lack of symmetry is then caused by incomplete filling of the EG orbitals. The 3 electrons in EG orbitals may be distributed as dz square 1 dx square minus y square 2 or dz square 2 and dx square minus y square 1. The symmetrical distribution dz square 2 dx square minus y square 2 would give a regular octahedral complex, but dz square 1 dx square minus y square 2 distribution differs by having 1 electron less than dz square orbital. As the orbital is directed along the z-axis, the ligands on the z-axis would be repelled less and drawn in towards if it contain only 1 electron. This resulting complex would in this way be slightly distorted, having 2 short bonds along the z-axis and 4 longer bonds along the xy axis. This figure indicates that these two situations, see there is the shortening along z-axis, that is elongation in xy axis, and in another there is shortening in xy axis and elongation in z-axis. These two situations will be explained how the unsymmetry will be affect if the dz square orbital is unsymmetrically filled and dx square minus y square orbitals are unsymmetrically filled. Alternatively, the electronic arrangement of dz square 1 dx square minus y square 1 has the shortage of one electron in the dx square minus y square orbital, which is directly along the x and y axis. Thus, ligands along the x and y axis are repelless. This distortion caused by such an arrangement of the electrons results in the complex with 4 short bonds in the xy direction and 2 longer bonds in z-axis. When the distortion of electron is dz square 1, dx square minus y square 2 has the repulsion between dx square minus y square 2 electrons and ligands along the x and y axis is more. This should be results in raising of the energy of the dx square minus y square orbital. Instead, the ligands along the x and y axis go away from the metal ion and reduce the repulsion between dx square minus y square and the ligand to such an extent that the dx square minus y square orbital becomes lower in energy than the dz square orbital. The 4 bonds along the x and y axis becomes longer and 2 bonds along the z axis become relatively shorter. Alternatively, when the distribution of electron is dz square 1, dx square minus y square 1, the repulsion between dz square 1 electrons and the ligands along the z-axis is more. This should be results in raising the energy of the dz square orbital. Instead, the ligands along z-axis go away from the metal ion and reducing the repulsion between dz square and the ligands get to such an extent that the orbitals becomes lower in energy than the dx square minus y square 1 orbital. The 2 bonds along the z-axis becomes shorter and 4 bonds along x and y axis becomes relatively shorter. There is no theoretical way of deciding which of the possible distortion is more likely, but the experimental result show that it is the arrangement of 4 short and 2 long bonds, that is the electronic arrangement dz square 2 dx square minus y square 1 predominates. In the crystal of copper second chloride, for example, each Cu2 plus ion is surrounded by 6 Cl minus ions, but 4 of them are at a distance of 0.23 nanometer, while the other 2 are at 0.295 nanometer away. Nickel second chloride has a similar crystal structure, but all the 6 Cl minus ions or ligands are equidistant from the central Ni2 plus ion. This is because the Ni2 plus ion with 8 d electrons and has a symmetrical arrangement of electrons, so that it forms perfectly symmetrical octahedral complex. See in the figure, see there is the particularly splitting of orbitals, ligands on z-axis moving out and ligands on z-axis moving in for tetragonal distorted octahedral complex. Similarly, copper second chloride has a distorted rutile structure in which 4 F ions or ligands are 193 nanometer away from the copper 2 plus ion, while the other two F minus ions are 0.227 nanometer away. Chromium second fluoride is like copper second, having distorted rutile structure in which there are 4 CRF bonds at 2 angstrom unit and 2 CRF bonds at 2.43 angstrom units. Such an octahedron is said to be tetragonally distorted. In figure, it is shown that general orbital splitting diagram in Jahn-Teller distortion. Generally, 10 dq is very greater than delta 1 and delta 1 is greater than delta 2. With reference to the above figure, energy calculations can be done for the D9 system copper second ion. The T2g orbitals are fully occupied. The net stabilization due to T2g is 0. See here, net stabilization energy for T2g is 0. The stabilization energy due to EG orbital is minus 1/2 delta 1 and net stabilization energy for the EG after calculation it is minus 1/2 delta 1. This net energy minus 1/2 delta 1 is called the Jahn-Teller stabilization energy and provides driving force for the distortion. Just as the removal of the degeneracy of 5d orbitals can result in crystal field stabilization, further removal of degeneracy of d orbital can result in additional stabilization. The Jahn-Teller effect is also observed in excited states of some complexes which in their ground state are a regular octahedron. To illustrate the effect on excited states, we may consider the TiH2O6 3+, FeH2O6 2+, and COF6 3-. The first of these has an excited state configuration EZ1. The presence of the simple EZ electron causes the excited state to be split, and it is this state which account for the broad flat counter of the absorption band of TiH2O6 3+. In both FeH2O6 2+, the ground state has the configuration T2G4 EZ2 and the excited state with the sum number of unpaired electrons has the configuration T2G3 EZ3. Thus, the excited state of these species are subject to Jahn-Teller splitting. It brings out the absorption transition, and this show two peaks in the absorption spectra of these ions.